And then came down to okay.
Does it work? Okay. Okay. Right, so I think that we can start. Today we're very happy to have Yichul Choi as a speaker. He's still a graduate student at Stony Brook. He will graduate in coming spring. But he will move to IAS for his first postdoc in the coming fall. So today we're going to talk about the quantization of the Axion-Gauge couplings and generalized symmetries. Okay, please take it.
Yeah, thank you, Gongsun, for introduction, and thank you for having me. Yeah, I'm very happy to be here to talk about our recent work on axion physics. So the talk will be based on these two papers in collaboration with Matthew Forslund. He's a student at Stony Brook. Lam, he's a postdoc at MIT. And Xuan Shao, he's my advisor at Stony Brook. So the talk will be divided into two parts. In the first part, I'll try to explain how the precise global structure of the standard model gauge group affects axion physics. The second part of the talk will be about generalized global symmetries, which I will briefly explain what they are, and some applications. Maybe as a disclaimer, I'm raised in the HepTH community, and this is my first attempt to try to connect to actual particle physics. So I'm very new to the topic, but I'll try my best to say something maybe of interest to people in the particle physics community. So let me begin slowly by asking the following question. What is the, okay, let me try to remove this actually. Okay. What is the gauge group of the standard model? If someone asked me this question, of course, my immediate answer would be, well, it's SU3 times SU2 times U1. However, is this really precise? Let's say you want to know not just the Lie algebra, but the actual Lie group for the standard model gauge group. And there is a slight subtlety. So more or less well-known fact, which is, although it's not very commonly discussed, is that if you take a certain G6 subgroup of SU3 times SU2U1, which is made out of certain combination of G3 center here, G2 center here, and some mod 6 element here, then you can find a subgroup under which every standard model particle that we know are neutral under this subgroup.
Excuse me, from SU3 and SU2, you take centers, right?
That's correct.
And from U1, some
special
element.
Yeah, some special element. Okay. Yes. So that is the subgroup, and because of this, for all we know from experiments, the actual gauge group for the standard model might not be just a simple product, but you can actually remove the G6 or any subgroup thereof by portioning out this G6 or a subgroup of it from this simple product form. So the gauge group of the standard model can be any of the following four options. I'm going to distinguish them by this label little q. Q can be any divisor of 6, and so these are the four possibilities. So essentially, these four distinct global forms of the standard model gauge group, they share the same local dynamics. What does that mean? We cannot really distinguish them in current experiments. So let me try to say more. Let me try to give you more intuition about it.
So let's speak about SU3. The quarks are in the fundamental representation. They react on the center, right?
Oh, yeah. So that's a great
So
question.
how would you eliminate the centers from the standard model?
Yeah. So the quarks are charged under the center, but they also carry hypercharge.
Yes.
In such a way, when you take a particular linear combination,
So you can say that it's possible to find.
Exactly.
So the center is compensated by the
Exactly.
impact charge. Okay. And the same with SU2.
Exactly. Yeah, that's exactly the case. Yeah. So if you want to distinguish these possibilities experimentally, then the simplest thing that you can hope for is that, let's say tomorrow we find a new particle, which is charged under, say, fundamental SU3, but neutral under SU2 and U1 hyper. Then you immediately rule out 2 equals to 6, because such a particle transforms non-trivially under the G6 subgroup. So that's the simplest thing you can hope for. But if we don't discover new particles like charged under G6, then it's a little bit hard to distinguish these different objects.
What kind of particle would it be that's charged under the C6?
Let's, for instance, maybe our may or may not comment on this later, but let's say in the concept of axion physics, let's say we take the KSPZ model in a simple setup, then there will be heavy PQ formula charged under the fundamental of SU3 and neutral under the other two factors. So this minimal KSPZ model is actually it cannot be realized with Q6.
But in general, if you had any vector line call, it would also be C6.
That is correct. Yeah, yeah, unless we assign some hypercharge to cancel that out. For anything charged under only as fundamental of SU3, we are not allowed to use Q6.
And also have some external object, not just a particle, which is not sensitive to this structure.
Not just particle, but what do you have in mind?
I don't know, some solitons or something, like, this is sort of a global structure, the application could be set up the local structure, and then in general, like, external object is
Extended objects. Let me see. So
It's good.
I don't. I just.
yeah, I don't have an immediate answer, but it's a yeah, interesting case. But okay, another comment is that many of the grand unified theories, for instance, SU5, SO10, etc., they require Q to be 6. I'm not going to explain the details, but it's a simple group theory that if you want to embed GSM into a bigger grand unified gauge group, then Q must be equal to 6 in many of the cases. Let me skip this part for later, but and what I'm going to tell you is that if you add an axion to the story, so let's say you have an axion and you try to couple that to the standard model gauge group, then the value of Q actually becomes important, as well explained.
Can you say something else about, so if you had SU5,
Yes.
why do you need to have Q equals to 6?
Yeah, I can maybe give an indication. So let's say we have a SU5 matrix, so 5, 5, 5 matrix. And the way the standard model gauge group is embedded is like we have a 3 by 3 block for SU3, 2 by 2 block for SU2. But U1 hyper is sort of embedded diagonally. So there is some identification between center of SU3 and U1 hyper, as well as center of SU2 and U1 hyper. And that's the modulation function. Another way to say is that yeah, maybe yeah, there's a sort of application. Oh, wait. Okay, good. Okay, so let me move on to actions. So for the first, say, 10 or 20 minutes of the talk, by an action, I always mean any periodic scalar field with periodicity 2 pi f. F is the action decay constant, which couples to the instant density ff tilde. Doesn't have to be explicit action for now. You can sometimes say I call action-like particles. And originally, actions were introduced or motivated to resolve the strong CP problem. And needless to say, nowadays, actions are one of the most well-motivated beyond standard model particle, which are active targets for experimental searches. So the generically, the coupling between an axion and gauge field A mu takes the following form. It couples to instantaneous densities with A f tilde. Here G is the gauge coupling constant and F is the axion decay constant. And importantly, we always have this coupling constant K, which in this talk I'm gonna refer to them as Axion-Gauge coupling. But in the literature, it's more common to call them anomaly coefficient because they correspond to some triangle diagram in the UV PQ realization. But for now, I'm not assuming the UV is PQ. So I prefer to just call it Axion-Gauge coupling. And then the thing about this K is that they cannot take any arbitrary real value. They must be quantized for the test integral to be well defined under the periodic identification of the axion, as I'll explain a little more. Before we do the full standard model, let's do a warm-up exercise. Let's try to distinguish SU2 versus SU3 gauge field. So it's an elementary fact that these two share the same Lie algebra, but they differ in their global structure. Our axion coupling looks like so. Let's try to figure out what's the quantization condition imposed on this K. So what do? We have a test integral, and let's try to shift axion by its periodicity. Inside the path integral from the exponentiated axion, such a shift is going to generate the following term. For the path integral to be well defined, or the path integral to be single valued under this periodic identification of axion, this vector that you generate, it must be equal to 1. What is this? We have 2 pi I k times this integral, and this integral is the instant number, as you can recognize. Now, so far, it's the same for SU2 and SU3. So how they differ in their instanton sectors. So if F was a SU2 gauge field strength, then my convention is such that the instanton number is always an integer. So this whole integral is an integer, and to satisfy this condition, the K can be an arbitrary integer as well. However, now let's say the gauge group was SO3, which is SU2 mod Z2. Famously, in the 70s, Tooth showed that in such a case, there are instantons with instanton number 1/2. These are called fractional instantons. So more generally, they can SO3 instantons can have any half integer instanton number. What does that mean? If we want to satisfy this condition, then now this can be 1/2. So K can only be an even integer. So this is how SU2 and SU3 are different in the presence of an axion.
So we are saying that if you allow for the algebra is the same, but you allow only integer number representation, spin 0, spin 1, and so on. You can build half integer. Is it related somehow with the fact that in SO3 instanton has 4 times larger reaction than in SU2?
Yeah, it's precisely that. Yeah,
It's precisely that.
Yeah.
Then I think it was also Wilczek who.
Oh, I see. So here are.
Yeah, maybe, yeah. I don't remember the year, but it has a short special paper on this.
I see.
topic.
I see. Yeah, thank you. So yeah, all right, we'll check here. Okay, so now let's try to move on to the first standard model. I'm gonna omit most of the technical details, but what is it? So now we have 3 gauge fields. So this is SU3, G is SU3, F is SU2 gauge field, P is the U1 hypergauge field. And my axion A generically couples to all 3 of them with 3 coupling constant K3, K2, and K1. This coupling constants needs to be quantized, and then the precise quantization condition is going to depend on the global form of the standard model gauge group. And before I show you the results, final comment is that it's also convenient to write down the axion coupling below the electroweak symmetry breaking scale in terms of the coupling to gluon, which is denoted as N, and coupling to the electromagnetic field denoted as E. It's because most of the experimental searches try to measure the coupling between axion and ENM field, so it's convenient to have this written down. So here N is related to K3, and E is just some linear combination of K2 and K. Yeah, how do they look like, the quantization conditions? So this is what you get. It's a little bit a lot, but yeah, I'm not going to explain all the technical details, but let me point out some features maybe. So maybe let's start from Q equals 1. So there is no quotient. The gauge group is just product of 3 Lie groups. In that case, individual couplings K3, K2, K1 can be arbitrary integers. There is no correlation between them. Now, maybe let's try Q equals 2. Then we are modeling out by a G2 subgroup, which is a combination of G2 center here and then some G2 element from U1 hyper. What happens is that the K3, K2, K1 still satisfy certain separate quantization conditions. But because now the subgroup we are modeling out is shared by SC2 and U1, there is a certain correlation between K2 and K1 that happens. And similarly for other cases. And I should point out this same set of results were reported in these 2 other papers that are posted about the same time as our paper on arXiv. Okay, so it's great that we can work out all these quantization conditions. It's good to know. But what do they buy us? What can we use them for? So now let me try to explain one thing we can do with these quantization conditions. But to make progress, I need to make some more assumptions. So the result that I showed in the previous slide, it's completely bottom-up. It's UV model independent. It's going to hold for any axion. It doesn't matter whether it comes from PQ symmetry breaking or extra dimension, etc. But from here on, let me make one more assumption. Let me assume that now my axion is a post-inflationary GCD axion. What does it mean? I am going to assume that my axion came from a PQ symmetry breaking. It's happened after inflation. And then I'm going to assume that the mass of the axion comes only from the coupling to QCD and nothing else. And I tried my best to connect to some experiment, and then experimentalists try to measure usually the effective coupling between the axion and photon, which is written as GA gamma gamma.
How do you measure it?
It's a great question. Actually, that I should know the answer to, but let me see. Yeah, I don't know how experimentally it's measured. I really should know. I apologize. But I grew up in Spring Street only needed 2 months, and I did carefully look at how experimental it is done. But okay.
One way to measure it is, I guess, the story would be that it's measured in the so-called scopes, and so, but you don't measure the coupling, you measure the product of the density and the strength, right? Because you need an extra assumption that this axion saturated the dark matter, right? We know the energy density of dark matter around us, but we don't know what fraction of it is made out of. So whatever you do, there will be an extra assumption that it's 100% of dark matter. Otherwise, it's modular to that assumption.
Okay. Yeah.
So maybe we have to, does that mean that we have to sort of know the black matter has a density around the scarp to the size.
Let's say it's going to like 30%, okay, people say, right? But even with that, right, you have to have an additional assumption, not just saturates. Otherwise, who knows?
Or in an ideal world, you can do a light shining through algebra, use and detect.
Well, that is usually not, I mean, many orders of magnitude away.
But once we know the frequency, I think there will be infinite resource.
Yeah.
But all I mean is simply that in the Lagrangian, I have GA gamma gamma A F or where F is the EM. That's I'm going to assume. Yeah.
And also another question, like, why is it important to assume that it is produced something, like, the pages which we're working is something.
Oh, yeah, so it'll become clear in later slides because they're related to the domain or problem. Only for post information reactions. Okay, so I'll try to constrain this GA gamma gamma. I'm going to take the result from this paper from 2016. It's carefully derive the GA gamma gamma using the higher Lagrangian. So it composed of two terms. MA is the mass of the axion. Roughly speaking, the first term comes from the bare coupling to the photon, and the second term comes from mixing with mesons.
But you also absorb the factor into the decay parts.
That is true. Yeah. But so there is a difference in convention. So my F doesn't have a factor of n, but their F has a factor of n. So there is a convention difference. Okay, so now let's see what we can do. So the GA gamma gamma depends on this ratio E over n. It's some rational number. But all we know, for all we know, it can be any rational number, and it doesn't seem to put any constraint on GA gamma gamma. Because the rational numbers are dense in real numbers. Let's try to say more by noticing first that this n is related to the number of axion domainers. In other words, here this n dw is the number of distinct minima in the axion potential. And the number of domainer is twice n, so this is my convention. Somehow it seems to be the standard convention in the literature that there is a factor of 2 difference. Anyways, n is the 1/2 of the number of domainers. And then if the axion is a post-inflationary axion, so if the PQ symmetry breaking happens after inflation, and it's gonna form domainers. And in the absence of other mechanisms, these stable domainers from after inflation can be inconsistent with what we observe nowadays, because their energy density, because the way their energy density redshift as the universe expands. So there can be all kinds of different mechanisms to solve this domainer problem, and in fact, it's an active area of research to think about domain problems. But what I'm going to do is to try to do the most simple-minded thing. This is to assume that the axion potential has only one single minimum. So I'm going to assume there is just no domainer. I'm going to set n dw equals to 1, which corresponds to n equals to 1/2. This is my first assumption, or maybe start the assumption. Another thing I want to say is that it's about the global form of the standard model gauge group. I'm going to focus on the case where there is a mod G6 in the denominator. And what is the motivation to do so? Let's say it was not G6, or maybe just the simple product. Then what that means is that as we go to high energy scales in the UV, there can be a massive charged particle charged under this G6 subgroup, as we discussed at the beginning of the talk. And when there are such particles, very heavy, maybe, what can happen is that since all the standard model particles are neutral under this G6, these heavy particles cannot easily decay into standard model particles. And there is a potentially they will form a stable valley, which may also contradict some of the observations. Again, there might be different ways to address this question, but the most simple-minded thing again that I can do is to forbid any such particles by saying my gauge group is this, and I just don't have to worry about any such potential issue. And with these assumptions, let's look at the formula again. So I set n equals to 1/2 to avoid any domain or problem. I assumed my gauge group is this to avoid any potential stable Rayleigh problem. And let me remind you with this global structure of the gauge group, in the previous big huge table that I showed you, there is one corner of the table saying that in this case, the coupling of the axion to the gluon and photon N and E must satisfy these quantization conditions. One check, I'm assuming n equals to 1/2, and then in fact the quantization condition can says that n can be any half condition.
Excuse me, if, for instance, n is 3 halves,
Yes.
then you will have several minima on the axion potential, more than one. And then you will have domain.
Yeah. So yeah. That's so I'm trying to avoid the domain or problem.
Okay.
Yeah. Yes. By setting n equals. That's right. Okay. So now we have these conditions, and then what we can show easily is that now n is fixed to be 1/2, and you plug in every possible value for E, satisfying these two conditions. Then you find that there is a lower bound on this ratio between the absolute value of J gamma gamma divided by the mass of the axion. From the quantization conditions and a set of assumptions that I laid out, you can derive a theoretical lower bound on this ratio. One comment is that this lower bound is saturated when E over N is equal to 8 over third. And whatever it's worth, it happens that this ratio 8 over third is the one that's realized by many of the gods, as well as the famous DFS model. So let me summarize what I told you so far in this explosion flow. So the vertical axis is the effective axion-photon coupling, and then the horizontal axis is the mass of the axion. And these colored regions are the places where it's ruled out by corresponding experiments. And these white and gray regions, they are currently not ruled out. And here I'm drawing a straight line which corresponds to this E over N equals to 8 over third. And what we have shown is that, assuming several things, that whenever you want to go to the gray region, you will have to address the domain or problem somehow, or worry about the stable Rayleigh problem.
Normally people add a bias potential in that region.
Oh, you mean, yeah. So that's one of the assumptions I guess. I assume the PCP, it's a PCP.
Exactly. You assume there's no bias potential, there's no gravity,
Yeah.
anything. Right? That's what.
Yeah, that's really changed this. So
Yeah.
we put, yeah.
So does that mean that if you allow yourself to have like a arbitrary domain one number, then this coupling can still be like 0, for instance?
Yes. So actually what happens is that in the previous formula, we can try to increase the value of it. Then this line start to move to left. But but we didn't emphasize that very much because as soon as the n becomes bigger, the error, so the bound becomes comparable to the error bar. So it becomes a little bit. So here my bound is 0.15, and there is this error bar. But when the n becomes bigger, the bound instead gets smaller, and then it becomes comparable to the error. So yeah, so.
Okay, so for different values of the n, you still have a bound.
We still have a bound.
Not 0.
That is right. That is right. Yes.
But the error is.
Yeah, but it's yeah, too little, yeah, too small.
Yeah, this.
Oh, this is coming from yeah. So yeah, here it comes from here. Yes. So all these numbers are some ratio up and down matrices, but it comes from evaluating them.
There's just one quick question. If you assume that global structure of standard mortgage group by the quotient group G6 and in KSV's model, that fermion should be charged under not only SU3 color, but everything, right? That you can make such a prediction.
So yeah, if Q is 6, then in KSVC,
then you should couple to it. You can make a prediction. You should couple to everything. SU3, SU3.
So not necessarily everything, but you can make it work by saying that it couples to SU3 as well as hypercharged, but it can still be neutral under SU2.
So it should be hypercharged. You agree?
That is right. Yeah, that's
but then it should be also charged under SU2 because it should be because Z6 should act on this fermion trivially, right?
That is right, and you can do that.
And once you say this is hypercharged, then I think this gives you a relation between isospin and hypercharge. So you cannot avoid having zero isospin for this.
So what I'm saying is that so in the KSVC, the KSVC fermion can be let's say you have this mode to 6. KSVC fermion can be in the following representation. Maybe it's fundamental of SU3, a neutral under SU2, and then if you choose the right value of hypercharge, then you can achieve this. You can find such a representation which is neutral under G6.
Yeah, I'm not sure. Given that non-Banach hypercharge, you can avoid having some non-zero form. Yeah, because okay, anyway.
Yeah.
You can discuss later.
Okay, yeah. Any other questions so far? Now I'm gonna switch gears to the second part if there are no other questions. Okay, so now in the rest of the time, I'm gonna talk about generalized symmetries. It's gonna be a little more formal. And let me first try to explain the basic idea of what they are. So in recent like 10 years or so, starting from this paper from 2014, in the FPH community and also in condensed matter physics and mathematics, there has been a lot of interest in attempts to generalize the notion of global symmetry in quantum field theories. And I really emphasize this is about global symmetries and not about gauge symmetries. I'm gonna say a little more, but the essential idea is to identify global symmetries with topological operators. And what does that mean? Let me try to begin slowly. So a symmetry that we all know and love in quantum field theory, one way that it manifests itself is as the existence of conserved quantities. Let me try to take a concrete example. Let's say we have a 3+1D QFT with a global U1 symmetry with a conserved nodal current, which I denote as J mu. So J mu is conserved, so B mu J mu vanishes. In differential commutation, D star J vanishes. Star is the Hodge star. So this is current. Well, how do we construct the corresponding symmetry operator? What you do is that let's first look at how to define a U1 charge. The charge is given by integrating your charge density, J naught, across the entire space. So that's your charge operator. And the symmetry operator is obtained by, as usual, exponentiating the charge operator with the angle alpha, which is the U1 group parameter. So this implements a finite U1 transformation on your Hilbert space. And thanks to the conservation equation, this U alpha is time independent. It's conserved under time evolution. How do you see that? If you hit U alpha with d dt, and dt goes here, the p0 active on j0, using conservation equation, it becomes the divergence of ji, where I is the spatial coordinates. Across the entire space, you have a total derivative and it vanishes. So that's a standard textbook material, but there's a little bit there is one small thing that is unsatisfactory with this expression, which is that we are not using the Lorentz invariance. So we are dealing with relativistic GFTs, and time is really on an equal footing as any other directions in space-time. So we have this Lorentz invariance, but the previous expression is not taking full advantage of the Lorentz invariance that we have, because as you see, to define the operator, we are picking a particular time slice. So the expression is not Lorentz covariant. Because of this, you can do a little better. You can try to come up with a Lorentz covariant expression, which is to pick an arbitrary three-dimensional submanifold M. In other words, it's codimension 1 in space-time, which is 4D. And then you can integrate your nodal current across this three manifold and then exponentiate it. When M is an entire space, it reduces to the previous expression, but you can think of such more general expression, which is fully Lorentz covariant. And thanks to the conservation equation, which says star J is closed, as you deform your manifold M a little bit, any correlation functions involving u sub alpha of M does not change its value. In other words, this operator, it becomes topological. It depends on the underlying manifold M only topologically. It doesn't care about the exact shape of M. What I just said is that the U1 symmetry gives rise to such a family of topological operators in your QFT.
This generalized usual notion, right?
That is right.
That's what it's saying.
But even more generalized. Yeah. So now we have this set of topological operators, and what you can do with them, one thing you can do is that you can put two topological operators next to each other. Since they are topological, it doesn't really matter how far they are apart from each other. And you can try to merge them into a single operator, which will again be topological. So what I'm trying to say is that in the set of topological operators in your QFT, there is a notion of multiplication. There is a multiplicative structure in this. This is called fusion algebra. So we say we fuse two topological operators. It sounds very fancy, but what it is just a U1 group multiplication. So if you have two U1 symmetry operators, U sub alpha and U sub beta, you merge them, you just do the group multiplication, which is alpha plus beta. And in particular, every such U alpha has an inverse. So you can fuse U alpha with U sub minus alpha, and it's going to become a trivial product. So the main idea here is that the notion of being conserved is really upgraded or promoted to the notion of being topological because of relativity. And the fact that symmetries lead to conserved quantities or topological quantities is the main reason that we care about symmetries so much. So now I'm going to reverse the logic and make the following definition. I'm going to define any topological operator in my QFT as a generalized symmetry operator. That's the most abstract definition of generalized symmetry. So whatever topological operator that you have in your theory. In this language, the ordinary symmetries that we know correspond to topological operators whose dimension is d minus 1, or codimension is 1. And the fusion algebra follows a group multiplication rule. But in a given QFT, if you look at topological operators, each of these red and blue conditions in general can be relaxed. So that's one point of to come up with such an abstract definition, because we can generalize it now. There are sort of two main directions to generalize this notion of symmetries. One is to consider topological operators whose codimension is p plus 1, where p is greater than 0. It's topological operators of lower dimensions. So these are called p-form symmetries or higher form symmetries in the literature. Another generalization is that you can have topological operators which do not follow any group multiplication rule. In the literature, these are usually called non-invertible symmetries because since they don't follow any group multiplication rule, in particular, the given operator may not have an inverse. And you can also have mixing between these two different notions. And using these jargons, the ordinary symmetries correspond to zero-form invertible symmetries.
The symmetric vector operator for the non-invertible symmetry, that should be also topological.
That should be topological. That is right.
So sometimes people talk about -1 forms.
Yeah.
What's that? Is that codimensions?
So it's hard to say what's the topological operator for -1 symmetry, but I'll tell you later. But the thing is that if you have a P-form symmetry, one thing you can think about is that there is a corresponding Euler current, which is P plus 1. If you take the whole square of that, then you have a B minus P minus 1 form current, which is conserved. If you set P to be -1, it becomes D form, and any D form in this space-time dimension is conserved. So what it means is that it corresponds to the parameters of your theory. So any free parameter of your Lagrangian is colloquially called -1 function. I saw some recent papers where people try to make it more precise, but yeah, that's what it is. Yeah. Okay, let me give you a very basic example of a generalized global symmetry. So the simplest example is actually something everyone is familiar with, which is just the Gauss law. So what is the Gauss law? So let's go to the free ENM, no dynamical matter fields. So we put a test charge, probe charge of electric charge Q, and we surround it by a closed surface, two-dimensional surface. And we integrate the electric flux. So this derive is just the phase rate to say E dot dA. And if you do this integral, you measure the charge of the surrounded particle, which in my convention is integer valued. And of course, the thing that we learned in our undergraduate is that the shape of this Gauss surface is not important. You can wiggle it however way you want. And phase way to say is that the surface is topological. And why is it topological? It's because the electric field is divergence free. So we have this equation of motion telling you that this surface is topological. And if you try to phrase this in a QFT language, what is the test charge? Test charge is just a Wilson line, which is the word line of this test particle, given by this expression. And what he just said is that this surface operator now, because we are doing QFT, it defines a topological surface operator. Namely, it's the charge of the Wilson line. To get the symmetry operator, as usual, I'm going to exponentiate the charge operator with this alpha, which is the U1 group parameter. And it defines for me a surface operator, two-dimensional operator, U sub alpha supported on this two-dimensional surface, sigma. Now the Gauss law says this surface operator is topological. It's a codimension 2 topological operator in my free Axion-Gauge theory. By definition, what is it? It's the one-form symmetry. It's an example of a one-form symmetry. In particular, this set of operators follows the U1 group multiplication rule. And since it measures the electric charge of the Wilson line, in the literature, it's commonly referred to as U1 electric one-form symmetry. So ordinary symmetries, in other words, zero-form symmetry, act on local point operators. They have a codimensional topological operator, and you surround your local operator by the codimensional surface and shrink it down to a point. That's how ordinary symmetries act on local operators. What about the one-form symmetry? Well, we already learned that the one-form symmetry, in this case, the electric one-form symmetry, is actually the Wilson line. So now I'm drawing a space-time picture. So you have your Wilson line extending along one direction. You can topologically link your Wilson line with this surface operator. Here, this orange line is really a two-dimensional surface. I'm not drawing one 2 dimensions. What the last law tells you is that as you shrink this operator, since it's topological, you can shrink this down to nothing at the cost of measuring the charge of the surrounded particle, in other words, a Wilson line. So it acts on the line operators in that way. And it was brought up before. Another simple way to think about one-form symmetries is in terms of its associated currents. So that there is another current for this one-form symmetry. It's a two-form instead of ordinary J mu. So it has two indices anti-symmetrized. And for this case of electric one-form symmetry, the corresponding nodal current is simply the field strength. And field strength is conserved because of the equation of motion. So this kind of one-form symmetry acts on line operators. More generally, if you have a p-form symmetry, they act on p-dimensional extended operators. And then they will correspond to nodal currents, which has p+1 many indices.
These are just compared to equation motion.
This is a equation of motion.
Equation motion.
Yes.
Bianchi identity.
I will say that in this slide. So that's a most elementary example of a one-form symmetry in a free abelian gauge theory. There is actually one more one-form symmetry in this theory, which is the electromagnetic dual version of the previous one. So this is called magnetic one-form symmetry. And since it's one-form symmetry, again, action line operators. And what are the lines in this case? They are the tooth lines, which are the wand lines of magnetic charges now. And since it's a one-form symmetry, there must be a corresponding topological surface operator. And these are given by this expression. Notice that compared to the previous operator, we are missing a star. So there's an electromagnetic dual version. And I'm putting a superscript M. We note that this is a magnetic one-form symmetry operator. And as Gongjon anticipated, the reason why this operator is topological is now not because of the equation of motion, but it's because of because df is 0. It's called Bianchi identity. And the corresponding nodal current is simply the dual field strength F dual. Let me try to make a few remarks about certain properties of one-form symmetries. As I said, they act on line operators, but they can never act on local operators. It's very simple to see that. In 4-dimensional spacetime, if you have a point operator in a topological surface, you can wiggle your topological surface whatever way you want and shrink it away without ever seeing this point operator. It dimensions just don't add up. So there is no way to non-trivially link a surface with a point in 4 dimensions. There are too many ambient dimensions. So one-form symmetry never act on local operators. What does that mean? Let's say you have a theory with a one-form symmetry. You want to break it. What can you do? First thing you can try is, can I add any local deformation, local operator to the theory? Would that break the one-form symmetry? The answer is it does not, because there is no local operator charged under this one-form symmetry. In other words, if you are doing a low energy FT, you see an emergent one-form symmetry. But unlike ordinary emergent symmetries, the emergent one-form symmetry is not going to be broken by any higher dimensional operators. It's exact in the series expansion over 1 by lambda, where lambda is your cutoff scale. Okay, then how do we break the one-form symmetry? Is it really sacred? Can you just not break it? That's not true. So let's go back to the electromagnetism example. So we have electric one-form symmetry, which came from this conservation equation, d star f equals to 0.
Excuse me, when you say d mu f mu is equal to 0,
Yes.
it's true only if you don't have charges somewhere.
Exactly. That's
If
why we
you
have
put some sources, then it's not true.
exactly. That's the next.
Okay, I'm sorry.
We're totally getting there.
Sorry.
Yeah. So when we have when you don't have any charged metals, we have the equation and we have one-form symmetry. But as soon as you introduce metal phase, the right-hand side will be will have the contribution from the mirror field, and it's not satisfied anymore. And your Gauss surface consequent rate is not the closure anymore. And the one function tree is now gone. So that's how you break the one function tree.
So a question. So you can implement also add the match to the orthogonal gauge for surprise. So I just mean that the 0.6 is not broken or something. Or...
That's it. So if you are giving mass through the Higgs mechanism, then the Higgs field will be charged under the that will play the role of this and break the one function tree.
But you can also do a structure there.
That's
In that case, like
yeah. Let me see. I guess yeah, but the point is that to break the one function tree, it might be the stopper field, or it might be split or anything else. But the point is that we do have to introduce new degrees of freedom. So we cannot break it without introducing the degrees of freedom.
Yeah, in a sense, like a massive photon has a natural degree freedom. So.
Exactly. Yeah. I get. Yeah, that's a great way to say it. Yes.
So in other words, your statement on the previous slide about having stable is really a statement that they're stable. You know, if you added higher dimensional operators composed of the degrees of freedom of the original theory.
That's right.
They're not stable to adding.
Exactly. That's the way to phrase it. Yeah. Okay, so yeah, let me make a few more further comments. So okay, so it's sort of a review of previous several slides. So let's consider in the infrared we have a free ENM. Let's try to UV complete it. In a way, at high energy scales, or these one function trees are explicitly broken. Let me call it E electric. This is defined E electric, which is the approximate energy scale above which the electric one function tree is explicitly broken. And how is that broken? As we discussed, to break it, you need additional degrees of freedom, and the breaking scale will be roughly equal to the mass scale for the electric degrees of freedom, which I denote as M electric. And similarly, I can define an energy scale in magnetic, below which you have emergent magnetic one-form symmetry, but above which it's explicitly broken by magnetically charged degrees of freedom whose mass is M magnetic. The E electric and E magnetic, of course, depends on the specific UV completion that you have in mind. And then there is no relation between these two scales. Depending on what is your UV completion, this can be much larger than this one, or vice versa. So that's the situation in free ENM. Now let me go back to the axion story. Now let me add the axion to the theory. So now I'm going to consider this simple model, which is called axion electrodynamics. So there are the degrees of freedom. I have the axion A, and I have the ENM field, my photon. And then the difference of full Lagrange. So it's a simple theory.
Yeah, what's the difference between the second and the third term?
Oh, difference is, so this
It's the
is
same every EM, right?
yeah. So this is like in
Okay. This is EM squared. I mean, EM FEM squared, and this is FF2. Okay.
Exactly. So this is the axion of the AN in some way.
Okay, I got it.
Yes. Okay, so before we had the axion, we had these two electric and magnetic one-form symmetries. Now that we added additional degrees of freedom, which is the axion, we need to reassess the situation. What happens to these one-form symmetries? Okay, let me first do the magnetic one-form symmetry. This came from the Bianchi identity written here. And the Bianchi identity doesn't change in the presence of the axion. So this still vanishes, and you still have a magnetic one-form symmetry. But what happens to the equation of motion? If you do d mu f mu nu, you can compute the equation of motion. And what you're going to find is the right-hand side now depends on d mu a f multiplied by the field strength, and it doesn't vanish. So naively, our conserved nodal form went away in the presence of the axion. And it looks like the electric one-function tree is just explicitly broken. However, there is a more to this story. Unfortunately, because of the time, I have to omit all the technical details. Let me just tell you the answer, what happens to the electric one-function tree. What happens to is that the previous Gauss surface operator is now not topological anymore if you have an axion, so naively the symmetry is gone. And you can make certain modification to this symmetry operator to define a new set of surface operators, which I call D instead of U. So these D operators, first of all, they are surface operators, so supported on two-dimensional surface. And this alpha is any rational endpoint. So you are taking like a rational subgroup of your original one. You can find a set of operators, and this set of topological operators, which comes from the original electric one-function tree. But there is a price to pay. What's the price to pay? Is that this D alpha operator is not invertible anymore. It doesn't follow any group multiplication rule anymore. So you still have topological operators, but they become non-invertible. And this is an example of a non-invertible one-function tree. More precisely, before we had an axion, we had these electric Gauss closed surfaces. We can take U dagger. It's a unitary operator, and it's one. But now this new symmetry operator, if I take D times D dagger, you have a sum over a bunch of magnetic surface operators, which are still topological, and with some additional contribution that I'm not going to explain.
So what is the difference between this axion case and the other higher dimension operator case? I think I'm asking because in both cases, you can sort of redefine the current, which is not conserved, right?
Yeah. So then this operator comes from that fact that your right-hand side is
let's redefine like F mu plus A F2 or something.
Yeah, that's the part that. Yeah, and then you need to do a little more work to define this deal.
I see. But so for instance, also, if you integrate out the electron within a QD, you will have a bunch of the higher dimension operators like Euler has and Lagrangians, and also there, I think that you have to modify the definition of the current.
So the difference is that in the axion case, this is locally. It's important that it's only locally, but not globally. But it's a total derivative locally. You can move it to the left-hand side, and then redefine your F mu to be basically A times F. If you have charged fermions, and what you will have on the right-hand side is the current, which is
no. I think I'm just integrating out the electrons, so I just forget about electrons. I'm just adding higher dimension operators to the.
Oh yeah, then it's the same story. You modify the.
Yeah, you modify that.
Yeah, but in this case there is a little more subtlety because you need to make sure that your modified current is not going to be case invariant.
Okay.
I mean, you need to fix that. That's where the non-invertible becomes. Exactly. That's the difference. Yeah. Okay, so.
Simple one-line question of why so before it was like a one symmetry, and now it's a discrete symmetry.
Yes, it's infinite discrete.
Is there a simple way to understand that thinking? That reduction?
It's a good question. So I don't have a particularly good answer. It might just be that it might be a limitation in our ability to find more symmetries, but we've only succeeded in finding discrete symmetries, but there might be more.
Is there any simple way to know what you're supposed to have on the right side in this vision algebra?
The way I presented it is totally mysterious. I just pulled it.
But what I'm saying is there any simple rule for us to figure out what you're supposed to have on the right side?
So I didn't write it down, but this D operator has an explicit expression. So I just write that expression down twice, do some manipulation. It's coming up. Yeah. So okay.
There's no rule.
There is no general rule. Yeah.
Expand it and then find it.
Yeah, that's how we did it. Yeah.
Excuse me.
Yes.
Can I ask you a rather naive question? Okay, it is known for a long time that the divergence of the F minute field strength tensor is equal, in normal theory without axions is just the current of the electric, which produces electric source. If you add axion, there is another term which is d mu times F mu. Then, okay, people considered this for, I don't know, almost half a century. So you reformulated it in the language of topological operators, but physically, is there any new compared to what people discussed for so long ago after this reformulation?
That's what I'll try to say. I mean, it might not be very new, but I'll try to see what we can learn from these topological operators. I'll say it's not a striking result, but you will see what I can say. Okay, so D was an electric one-function tree operator, which is now known in Markov. And when you fuse two of them, more precisely the D dagger, you get some of our bunch of magnetic symmetry operator. What does this mean? Before we had an axion, the two U1 symmetries were just completely independent of each other. But now they are not anymore, because when you fuse two electric symmetry operators, on the right-hand side, you can get magnetic symmetry operators. What does it mean? If you break the magnetic symmetry operator, then the left-hand side will be automatically broken as well. In other words, we cannot have D without having used superscript M. So in fact, it's a very common situation in the study of generalized global symmetries, where we have different kinds of symmetries. Some of them are more like parent symmetries, and some others are like child symmetries, in the sense that the child symmetries cannot exist without the other parent symmetries. So in our example, the parent is the magnetic one-function symmetry, and the child is the electric one-function symmetry. And what does it mean physically? Now, let's try to UV complete the axion electrodynamics. In such a way, all these symmetries are explicitly broken as some high energy scales. So as before, we have two energy scales for electric one-function tree breaking scale, and then there is a magnetic one-function tree breaking scale. So as you go up in the energy, because these two symmetries are not independent of each other, you are forced to break them in the right order. So since you need to basically break the child first, and then you can break parent. The child cannot use without a parent. So E electric, because of that, must be less than E magnetic. More physically, what does it mean? E electric is basically the mass scale set by the massive electrically charged particle, and E magnetic is the mass of magnetically charged particles. So you want that magnetically charged particles must be heavier than electrically charged particles. So at the level of a slogan, I can say, when you have an axion, monopoles must be heavier than electrons. Sounds a little bit trivial. Of course, monopoles are expected to be heavier, but not quite. If you don't have an axion, then in the IR, we have electromagnetic duality. So priori, there is no relation between these two. So it's really because you have an axion, you have such a hierarchy between the different mass states. Another comment, this is a universal statement in the sense that this followed solely from the symmetry structure in the infrared. I didn't assume anything about UV completion. This inequality must be satisfied in arbitrary UV completion of axion electrodynamics. And I didn't have time to explain this one, but you can also similarly show that the mass of the electrically charged particle must be smaller than the scale set by the axion string tension. If it's the PQ axion, then it's going to be a PQ scale.
What is axion string tension? What do you mean there by the axion string?
Energy density. Energy density. Tension of the axions.
You mean by string? You mean?
Oh, so axion string is the it's a one-dimensional object in space, and then as you go around this string, your axial field has a non-trivial winding number. That's what I mean by axions.
The string is made not from axions, from something else.
It's a polyphonic object.
Yeah.
Okay, so I don't have time to explain all the details for what happens when you do the first standard model, but I'll just show you the result. So to consider the entire standard model offered to a single axion, you can similarly show various hierarchical structure between different symmetries. This is a result. I don't expect you to know what they mean, but let me just comment maybe one thing. So the detailed symmetry structure depends a lot on what is precisely your gauge group. It also depends on the values of these quantized couplings. And final remark, if you set 3 equals to 6, there are still a lot of generalized symmetries, but to the best of our knowledge, we couldn't find any hierarchical structure of these parent and child symmetries. Okay, with that, let me conclude. So in the first part of the talk, we discussed the quantization conditions imposed on various Axion-Gauge couplings that depend on the precise global form of the standard model gauge group. In the simplest setting, if we want to avoid the Weinberg problem and also the stable relic problem, we could derive a lower bound on the ratio between GA gamma over MA. And oftentimes it's the case that whenever there is an axion, generically we find a lot of generalized global symmetries, and there are certain hierarchies between them. And these hierarchies between different symmetries lead to hierarchies between different mesh scales involving monopoles and axion strings. Okay, with that, I'll end my talk, and thank you so much for your attention.
Ask one question. I'm a simple-minded person. Assume I don't know about this extra generalized symmetries. I would still say that there is our nature prompts us that monopoles, if they exist at all, they might not exist in nature, right? Must be much heavier. Because we know the Witten effect in the monopole background. If you have kind of axion field, which may be not vanishing in the process, then the monopoles acquire electric charges, which are no longer quantized, and we don't see this in nature. So that if you wish, it's a simple-minded explanation why we don't see, monopoles are probably can be ruled out in this way, even in the visible part of the universe, right? Because then we should have some consequences of seeing diodes too. And diodes are electrically charged. And then they collide, they emit light. And this is a wrong type of light, I mean.
So you're completely right that there are many, perhaps much simpler ways to argue for such inequalities. And what I'm presenting to you is like a very sophisticated way to derive something that is already expected. I completely agree. So yeah, it is what it is, and yeah, indeed, it's something we think about day and night. Can you do that, or can you
okay, I understand that sometimes it's nice to have a more generic kind of, maybe it might be used in the future.
So the state of the affair is that for now we are sort of trying to analyze generalized symmetries, and we are rediscovering the things that are previously known in one way or the other. And yeah, it's our future job to have a new predictions that will be really good.
Okay, thank you. Does anything change when you have more axioms though? Because in string theory, people talk about axioms.
Yeah, there's a lot more things written. So yeah, I presented is the simplest thing with only one axiom. So the generic picture will remain, but the details will change. Like precisely what are the symmetries, etc.
Just one quick question to clarify the meaning of the axiom string. Suppose you don't have, suppose you have axiom model, you will come with the axiom model where axiom is not coming from Petrkin scalar. So there's no radial component, okay? But then in that case, do you still have a two-form axion winding symmetry in the theory?
Yes.
You do have, I think so.
Yeah,
but what does it mean by axion string? It's not the cosmic string coming from Petrkin breaking.
Yeah. So in the
how do I understand this axion string in the absence of the radial component?
Yeah, at low energies, it's just a solitonic object, right? It's a defect around which the axiom field winds around. In the UV model, if it's not PQ, but that I don't have a good answer. Right? I guess it depends on precisely which UV completion that we have in mind.
Suppose that I have axiom model, UV component axiom model, where axiom is not coming from Petchkin's complex scale, but axiom is just single degrees of freedom. But then in that case, I don't have a Petchkin complex scale. I don't have a Petchkin.
Yeah, one thing.
So
Yeah, I guess one thing that can happen is that yeah, in the UV, if you don't have dynamical strings because of the particular UV completion that you chose, then you just have this two-form symmetry all the way to your UV scale. So it's similar to previous things. So if you want to break the magnetic one-form symmetry, then you need to introduce dynamical monopores. But if there are just no dynamical monopores whatsoever at arbitrary high energy, then this symmetry will just persist. Similarly here, I didn't discuss this, but there is this winding two-form symmetry. And to break this two-form symmetry, you need to introduce dynamical strings. If your UV completion doesn't have dynamical string, then it's gonna just stay there. Yeah. Yeah.
So in your first part, about computing, if I have a mini charged particle in the universe, my biggest quotient group would be right. Yeah. So your correlation and conclusion about the minimal coupling photon will be gone, and I will not have trouble to have some stable value of mini charged particles.
Yeah, actually, let me see.
So relations are fragile.
Yes, it might be related. So to be honest, because I'm new to sort of these things, I'm infinitely confused about milli-charged particles. But one thing is that it's in all our discussions, it's important that this U1 is really U1. It cannot be R. If it's R gauge symmetry, then charge quantization will not be there, and also all the things.
Yeah,
but it's not gonna be there. Yeah, that's right.
And in the second part, you skip to the final table, just to understand, you can define this non-invertible symmetry as infinite series of, rational numbers.
That's right, that's right.
What's the meaning of this table? You're saying if the higher group of standard model is in the left, what's the realized non-invertible symmetry?
So the way to read this table is that the Q is the global structure of the gauge group. And then you go to each entries, and then, okay, let's say Q is 1. And if you see that, so this is above the electroweak symmetry breaking scale, and this is below the electroweak symmetry breaking scale. If you go there and then you ask whether this number is 0 mod K or not. If it's 0, then there is no higher group. If it's non-zero, then there is a higher group. Similarly here, if it's 0 mod 6, there is no non-invertible symmetry. If it's not 0 mod 6, then there is one invertible symmetry, and similarly for on the other entries. Yeah.
So you argue that mass of the electric, the energy scale of the electric seems to breaking below the magnetic seems to breaking. But what happens if you try to consider a theory whether reverse?
No, in the UV.
Yeah.
The claim is that in the infrared, it's not gonna look like extreme electrodynamics.
Oh, but it's like there is no like anomaly in this theory or like inconsistency.
No, it's not.
But it's
There's nothing wrong about such a theory to consider, but it's also that in the infrared, it's not going to be extreme electrodynamics.
So maybe not that related to the topic, but you mentioned this fractional instant one. Right. So and then also in the the standard model case, I said because you have sort of a similar structure, like you also have a similar structure, like a similar kind of instanton. If you divide by like say 2 and so on.
Sorry, I'm not sure if I got it. So can you say that?
So like you say that SU2 case and so 3 case you have a difference, and so 3 case you have the fractional instanton. So if you say that some model is divided by Z6, then you have a similar object.
Oh yeah. So there are Similarly, for these cases there are fractional instances. I forgot to cite this paper, but I should remember the authors. But there is a recent paper which studied fractional instanton for standard model with all possibilities. Very carefully. I can tell you later.
And then instanton case, we know that if you produce instanton, for instance, a collider, of course, this is kind of exponential separation or something. But if you produce it, then you have you produce all generations like a left, right, and so something, right?
left hand.
left and right, box.
Uh-huh.
I think, because each block has this one equation.
Mhm.
And then what happens for fraction instanton? I think I'm kind of curious.
Oh, yes.
In the principle, where we can see
That's a good question. So
at the sample going.
there was one thing that I didn't explain about the fractional instances, but maybe I'll go back to the SO3 versus SO2. So the thing about the fractional instanton for say SO3 is that to have a non-trivial fractional instanton configuration, there n is my space-time manifold. M must have a non-trivial topology. So for instance, if M is a four-dimensional torus, then you can find the fractional instanton solution which says instanton number 100. But if it's just R3,1 or R4, it will be relevant for collider experiments, and you are not going to see fractional instantons.
And that's what's supposed to have in the paper you look at.
That is right.
Sorry.
And he imports this fifth file. But yeah, one comment I want to make is that some people may object that why do I need to consider such topologically non-trivial space-time manifolds if we don't see them around us? So it's a general principle that I'm taking, which is that whatever low energy effective field theory that I have, independent of whether I can do experiment in curved space or with non-trivial topology or not, I'm going to demand my EFT must be consistent in any non-trivial topological space-time. And there is a good example for this, which is the which comes from condensed matter physics. It's the Economor effect. Integer Economor effect, more precisely. So what's the effective Lagrangian describing Economor effect? It's the Chern-Simons-Stam ADA, where A is the electromagnetic. And famously, the coefficient in front of ADA is the Hall conductance, which is experimentally measured to be a quantized set of values. So it cannot be any arbitrary number. And from the theoretical point of view, why is it the case? It's because unless the coefficient is quantized, the theory is not case invariant when your space-time has a non-trivial topology. However, the experiment is done in a more sample which don't have any non-trivial topology. So it seems to be the case, and this to mean that no matter what experiments we can do, it seems to be the rule of nature that whatever EFT we see must be able to consistently define for non-trivial topology. And it's verified in the quantum effect, and there are more examples. I will stop there.
Thank you so much. So let's give a big applause to
There was an old paper, I want to tell you, there was an old paper of Linde, very early of his papers, where he insisted since our world has a horizon, our world should be considered as compact. And then this has some impact on axions, on the what we can observe from the theta dependence and so on. But it seems rather strange to me that whatever happens at the edges of what we see of our universe can impact what we see here. It would be totally, well, counter everything we know, unless you stand at the point, there was this Mach's idea that it does impact the distant stars and whatever do impact what we see here, but it's a religion. It's not. There was no.
Yeah, I totally agree. It's very mysterious. It seems to be the case in say quantum effect and in kind of.
Yeah. Okay, I want to take a picture of you against one of your slides.
Oh, sure. Yeah, thank you.
Usually when I take a picture of the seminar speaker, come closer.
Yeah,
Or maybe put it on the first slide. Can you put it on the, okay. Come closer so it's not so visible.
Yeah, but then,
But you may smile.
You don't
Okay, thank you.
Thank you so much. Thank you. Yeah, can I have that picture?
Yeah, I can send you. Write me, please. Oh, Tony is good. Write me your email
Right.
address. I will give you a pen. Just a second.
I found it actually.
Okay, have a pen? Oh, yes. Okay, okay, okay.
Misha, here is your phone.
Huh?
Here is your phone.
Ah, okay. I put it here. Oh, sorry. But if you found, that's okay.
You read so much. Yeah, you don't measure them.
Okay, thank you very much.
Thank you so much.
But if you are interested, I can also find the reference.
Yeah,
to
that would be
it.
great.
It's one of his earliest papers. And I frankly speaking, don't know whether other people later discuss it, because indeed, if you say our world is in fact compact, and topology changes,
Right.
and there is maybe some different boundary conditions,
Right.
or maybe we cannot even know the boundary conditions, right? If we, let's say this is for certain, we cannot go beyond our horizon, right? Because this limit, if we cannot, I mean, the ray of light cannot reach it from us, for instance, how can we know if the boundary conditions are important?
Right.
How do we know the true boundary conditions? But this will, of course, violate locality, because we believe that if we do, for instance, experiments in this room, and then the real world doesn't. Well, there is an exception. If you have totally like in QED, you have massless particles, photons, and then they can be copiously produced. And because of this, there are infrared logarithmic. In some effects, there are infrared logarithms. If you say that the volume of the room is infinite, these are actual infinities. But instead, there's something we put the size of the laboratory, which determined what logarithm is cut off and the moment of 1 over L.
That's right.
But maybe something else in the scale, something like this in the scale of the whole universe. And if we don't know the boundary conditions, and they are important, and there is no way to know them,
Right.
but they are important for the result, then I mean, it's the end of science, right?
Thank you so much.
Thanks, Misha, for coming.
Great talk.
Thank you. Yeah. Very nice. Thank you so much. Thank you for inviting me again.
We appreciate it.
Thank you.
Let's go. Yeah.
Okay. Yeah. Disconnect.